Mm, Thank you for attending our event. I'd like to welcome all participants once again to the sixth webinar under our East 101 webinar series. We are glad to see you here. If you like our content, we hope you will help us by spreading the word. Today's topic would be Introduction to Pipenet for Liquid Pressure Surge Analysis by Mr. Kevin Chu, who is a process simulation engineer with East 101. So, for those of you who might be new to East 101, we are a specialty consulting company focused on providing advanced process engineering and flow assurance consultancy services to the oil and gas industry through process simulation technology. We were founded in the year 2003 by engineer Rafael Elias, and we have our main office in Kuala Lumpur as well as support uh, offices around the world. Our track record includes projects covering transient or dynamic simulation based engineering services for design and troubleshooting. You see flow assurance analysis up there as well. Operational assistance, especially operator training simulations, OTS, is something that is very important for safe and cost-efficient operation, which we gladly offer those services as well. And process simulation training, which would cover steady state and dynamic simulation, how to use the software, how to effectively use solve problems with simulations. Our clients, as you can see, include Shell, Petronas, and several others. For any inquiries about our services, please contact either myself, Zihong, or my colleague Avinash at the numbers and email addresses shown. More information is available on our website, east101.com. So this being the sixth installment in our East 101 webinar series, uh, you may know that we hope to cover a wide range of topics in this series, from upstream process design to downstream and refining, monitoring and surveillance, as well as analytics and AI. The webinars are scheduled to take place every other Wednesday from 4 p.m. to 5 p.m. Malaysian time. So that's GMT plus 8. And we already have our next talk lined up. The topic is biochemical reactor modeling using machine learning. The speaker, as you can see, is the beautiful Miss Madeline Balachandran, one of our best graduates from the internship program at East 101, with bright future ahead of her. Kindly mark your calendars for 9th of September, 4 to 5 p.m. Malaysian time. Before I introduce today's speaker and topic, here are some of the housekeeping items to take note. We will have one speaker this evening, speaking for about an hour, followed by a Q&A session. We kindly request everyone to stay muted to avoid noise and interference. If you have any questions throughout the presentation, feel free to put them in the chat box, and you will be addressed by the presenter at the end of the webinar. Speaking of the chat box, I would. Speaking of the chat box, I would like to drop our sales contact for your reference. Earlier, we brought that up, but this one is for your reference. So, and yeah, so if you have any questions, please leave them in the chat box. And if you have any difficulties with the stream, you might want to reconnect to the webinar, disconnect and reconnect using the same link And if you miss anything, don't worry. The recordings will be available within a week on our webpage under the Events tab. The speaker for today, Mr. Kevin Chu, is Mr. Kevin Chu is a process engineer at ACE 101. He holds a MEng, a Master in Engineering, in Chemical Engineering from University of Nottingham, Malaysia campus. And in his 4 years of industry experience, he has acquired expertise in a wide range of simulation software, including Pipenet for an LNG plant, HYSYS, and Aspen Utilities Planner. Without further ado, before that, you'll be joined by our panelist, Mr. Dr. Anwar Hamid, who is our process engineering manager at ACE 101. He's a simulation specialist with over 10 years of simulation experience. And he holds a PhD in computational study and advanced recovery from Imperial College London. And currently serves as industrial advisor and adjunct lecturer for the UCSI University. So during the Q&A session, Mr. Kevin and Dr. Anwar will be sharing the session to answer any questions that any participants may have. So look forward to that. All right, without further ado, I'll invite Mr. Kevin Chu to share their expertise and know-how with us.
Okay. Thank you, Ziho. Greetings, everyone. Thank you very much for your time to join today's webinar series. Again, my name is Kevin, and I will be the presenter for today's webinar. So our topic today, our topic today is introductions to Pipenet for liquid search analysis. So in this webinar, we will run through some of the basic concepts of liquid search and also demonstrate the hydraulic computation using Pipenet. So what is liquid search? So liquid pressure search is basically a transient sudden increase or decrease of pressure in a liquid pipeline. So one of the most well-known liquid pressure search is water hammer. So water hammer is a commonly observed phenomena taking place in any liquid transportation systems. So by definitions, water hammer is a pressure surge or wave resulting when a fluid in motion is forced to stop or change direction suddenly. And water hammer is commonly occurs when a valve is closed suddenly at the end of a pipeline system. And water hammer can generate a pressure wave and propagate, and this pressure wave will propagate in the pipe. So this image shows how the water hammer looks like in the schematic form. So we will discuss more on this after this. So before we talk about the theory of the water hammer, so let's watch a video on how the water hammer looks like in reality.
If the initial velocity of the water is very high, the initial pressure rise can be so great as to cause rupture of the pipe. Conversely, the reduction in pressure, when the wave becomes negative, can produce cavitation of the liquid, as seen here in slow motion. The initial vapor pocket thereafter collapsing against the valve and then tending to reform repeatedly. Because of the noise that is produced by the sound wave in either case, the phenomenon is very aptly called water hammer. Hold the pressure will very effectively cushion the pressure.
Yeah, sorry. So it's a very short video, so we just want to show how the water hammers look like. So from the previous video, Initially, the valve is open. Sorry. So initially, the valve is open and the water is moving to the left from the right to the left across the valve. So when the guy suddenly closes the valve, the water bounces away from the valve body. So the water will bounce away from the valve body towards the right. So this is because water is incompressible. So in order to conserve the momentum, the water have to move in a reverse direction. So initially they are moving towards the left. Now after the valve is closed, it bounces off away from the valve body. So that's why the water is moving in the reverse directions. So this is similar to the car collision example in our high school class when we were learning momentum. So when the water is bounced back, it create a vacuum region. So you can see that there's a like some sort of a vapor column here. So we also call it a vacuum region here. So this vacuum can form water bubbles in the piping. So, and because of this vacuum region, the water which previously moved away from the valve body will move back towards the valve body due to the pressure difference, and the water will smash against the valve. So previously the water moved in the reverse direction. Now because now you have a region formed at the inlet of the valve, then the water will move towards the valve body again due to the pressure difference. So if the liquid has a very high inertia, the smashing against the valve can be very catastrophic to the liquid system. So after that, the water will move back and forth. So the water will then move back and forth and repeatedly smashes against the valve until all its momentum is lost. So that is how the water hammers behave when you suddenly shut the valve. So where does the water hammer typically occur? So it can happen in water distribution systems, power station cooling system, oil pipelines, but most importantly, it can happen in any fluid system in which the inertia of the fluid is significant. So what are the consequences of water hammer? So water hammer can create a pressure wave in the piping. So as we mentioned earlier, so this pressure wave can cause major problems such as noise and vibrations, pipe rupture or collapse, and also cause cavitations in the piping. So in this session, I would like to introduce Nikolai Zhukovsky. So Zhukovsky was a Russian scientist, mathematician, and also an engineer. So he is well known as the founding father of modern aero and hydrodynamics. So one of the Zhukovsky's greatest achievement is his discovery of the water hammer theory. So he discovered that the pressure rise in a water line is directly related to the change in the fluid velocity, the wave speed of the fluid, and also the fluid density. Then based on this discovery, he came out with a simplified equations we call the Joukowsky equations. So which is the pressure, the delta P, the pressure change is equals to the fluid density multiplied by the wave speed of the fluid and also the change in fluid velocity. So this equation is also known as the instantaneous water hammer equations, as it can identify the maximum pressure when the valve is closed instantaneously. This equation is also very powerful as it allows us to estimate the maximum pressure surge during a liquid pressure surge event. So to understand how the liquid pressure surge looks like, so let's look at this case. So we have a reservoir tank connecting to a 20-meter piping. At the end of the piping, there is a shutdown valve. So we want to see what happened to the system when we immediately close the shutdown valve. So this is how the transient response generated using Pipenet looks like. So when the valve is closed about at the 1 seconds, so a pressure wave is generated and oscillates at the inlet of the valve. So you also notice that the amplitude of the pressure wave decreases over time. This is because the fluid has gradually lost its momentum. Next, we also try to use Joukowsky equation to calculate the peak pressure and compare it against the result generated by Pipenet. So we can see that the maximum pressure of the first spike is consistent with the maximum pressure estimated using Joukowsky's equation. So they are consistent with each other. So this proves that how powerful is Joukowsky equations. And other than a high pressure excursion, we also concerns of the low pressure excursions due to the pressure wave. So as you can see, the minimum pressure of the pressure wave goes below the vapor pressure of the fluid. So one thing we also want to like some to make sure of is the negative pressure spike that went below the vapor pressure here is actually artificial. So in reality, the water at that point will vaporize and we will not get that pressure in the system. So and then this low pressure excursion can cause operating issue to the water line. So the low pressure excursion, or rather we call it the negative pressure, cannot be lower than the vapor pressure of the fluid. If the pressure falls below the vapor pressure, a vapor bubble can be formed. And when the pressures recover, the bubble collapses and it can produce a shock wave. So let's look at some of the example where the negative pressure can occur. So earlier, when we look at the water hammer, when we discuss about the water hammer, we only focus on the upstream of the valve. So here, let's say let's assume that the left hand side is the upstream of your valve. So initially your liquid is moving from left to right. So suddenly when I close the valve, then this phenomena is what we see in the previous video or previous slides. But then what happened in the downstream is when the valve is closed, the water at the downstream will move away from the valve. So this is due to the inertia and therefore creating a negative pressure region at the downstream of the valve. So this can cause it can form a negative pressure region here. So another example is when we have a siphon system. So in this system, typically we have a pump delivering the liquid through a high elevations piping before sending it out to the atmospheric environment. So the negative pressure is typically formed at the high piping elevations. So what happened here is that at the high elevations, the water experiences high gravitational forces. And based on Bernoulli's equation, this high elevation can lead to the formation of a vacuum region at the piping. We will look at this in more details in the later session. So after witnessing how troublesome liquid pressure surge or water hammer can be, we need to know how to deal with that. So looking at the Joukowsky equation again, in order to minimize the change in the pressure, which is the term at the left hand side of the equations, so we need to ensure that the flow velocity is low, and also we need to use a slow closing valve. And we also can reduce the wave speed, which is the A term here, by using a shorter length of straight pipe. So how do we do that? i.e. we can add more elbows to the piping. So this can reduce the wave speed significantly. And nonetheless, we can also use a high pipeline pressure rating. However, as this is a very expensive way to mitigate that. So other than this, there are also equipment out there to help to eliminate, reduce or eliminate the water hammer effects, such as the accumulator, blow-off valve, surge tank, and etc., and many more. So Here, I want to share an incident related to a liquid pressure surge or water hammer, which is the Sayano-Shushenskaya hydro disaster. So Sayano-Shushenskaya is one of the largest hydroelectric dam in Russia. It is located in southern Siberia. So this incident happened in 2009, about 11 years ago. So let's watch a video regarding this incident.
This mobile phone footage of the disaster at Russia's biggest hydroelectric power shows the moment it was devastated. The images were taken from just a few hundred meters away. Filmed just after the explosion, fountains of water can be seen pouring from the base of the facility. What appears to be electrical flashes are silhouetted in the windows. The blast killed 12 people and more than 60 are still missing. Well, for more, we're now joined live by our correspondent Alexei Yereshevsky. Alexei, now we've got shots from the very moment of the explosion. What are the authorities saying about what actually happened?
Indeed, Alice, for the time being, the main reason viewed by the authorities for this incident is the destruction of turbine caused by the so-called hydraulic impact. To prove this point, there's been an amateur video uploaded into the internet to see what happened. Now, as you can see, this eyewitness footage was taken with a mobile phone. The quality is poor, but you can still see the power plant just moments after the explosion. And if we zoom in into the footage, we can clearly see the powerful head of water and explosions. It's what appears to have happened is the water, which normally flows from the dam through the generators, surged, and it damaged one of the electrical generators and flooded the vast machine hall which houses all of the electrical equipment. Now, some of the oil was released into the river, into the Yenisei River, but the plant itself was badly damaged. And
sorry, I need to stop that. So because so looking at the I think a schematic diagram here. So we can see that it was believed that there was a malfunction in the turbine, and the flow was suddenly stopped, and it led to the water hammer or liquid pressure surge in the systems. So that's why these accidents happens. So let's continue the video again.
Part of the roof was blown off. Now the generator hall itself looks like the aftermath of a battlefield. Now, indeed, the rescue operation is still continuing to rescue around 64 people who are still missing. We have received information of 12 people dead following this incident and a dozen more injured. This incident at the Sayano-Shushenskaya hydropower plant has already been described as the biggest in modern Russian history. Indeed, the consequences of it will be very serious for the region, with electricity shortages are to be expected, and also the costs of electricity can rise up to 5 times. Experts are already saying that it, of course, may take several years to repair all the damage and millions of US dollars as well.
All right, for now, Alexei Yereshevsky, thank you very much for...
Okay, so in the previous video, the correspondent Alexis, he mentioned that the incident was caused by the disruptions of the turbine due to the hydraulic impact. So let's look at the aftermath of this incident. So this image shows the hydroelectric facilities before the incident. And this image shows the facility after the incident. So this is the same locations. So you can compare both images and see that the whole roof was blown off after the by the liquid surge after the incident. So the following image shows the disrupted turbine, which is the main cause of the incident. So what were the possible causes for this incident? So there is no official investigation report. But then there are several speculations from various sources. So based on these speculations, the possible cause can be either due to incorrect startup process of the turbine, the excess load of the turbine caused by peak consumption, or the operators operate the plant at its maximum load when the turbines are vibrating, or it due to the manufacturing defect in the turbine. So, or maybe it can be due to the combination of one of these causes. So it's just speculations. So these are the possible causes which ultimately resulted in the sudden stoppage of water, which then led to the water hammer or liquid pressure surge in the system. So this shows how disastrous the liquid pressure surge can be, especially if you have if the initial of the fluid is very high when it was not handled properly. So in these sessions, we are using Pipenet to demonstrate the hydraulic computations for a liquid pressure surge event. So a little bit background of Pipenet. So Pipenet is basically a hydraulic computation software owned by a UK-based company called Sunrise Systems Limited. Oh, sorry. So it was developed. It was developed in University of Cambridge in 1977.
It's fine, it's fine. I'm going. Where to go start?
So let's look at the comparisons between Pipenet and HYSYS and also Olga. So before that, a little bit of a brief introductions to Olga for those who are not familiar with Olga. So Olga is a commercial software used mainly for flow assurance, and it is very good for multi-phase hydraulic computation. So it is owned by Schlumberger. And we did a comparison, the comparisons on this software based on the following properties like fluid flash calculation, fluid characteristics, rigorous hydraulic computation, heat calculations, and also the application and also their alternative software. So I will go through that one by one. So in terms of fluid, so the first row here. So Pipenet can only be used for single liquid phase, and HYSYS and Olga can be used for multi-phase system. And Pipenet does not have flash calculations, and whereas the HYSYS and Olga have flash calculations. And for Olga, is flash calculation was based on PVT table. For fluid characterizations in Pipenet, the fluid is defined by just specifying the density, viscosity, temperature, bulk modulus, and also the vapor pressure. Whereas in HYSYS, we have a component data bank which have all the properties predefined, provided if it's not a hypothetical components. And in Olga, we will use the PVT table again for the fluid characterizations. So for the rigorous hydraulic computation, so both Pipenet and Olga have the capabilities to perform rigorous hydraulic computation, while HYSYS do not, which I will explain later. Oh, sorry. So as for the heat calculations, in Pipenet, it will assume an isothermal conditions, whereas in HYSYS and Olga, they will include the energy balance calculations. So in terms of applications, Pipenet is typically used for single-phase liquid transients analysis, such as liquid pressure surge, water hammer, and etc. So HYSYS is typically used for process simulations, and Olga is typically used for flow assurance analysis. So there are many other alternatives in the market. So to perform computations based on the application. So the alternative for Pipenet is R, AFT Impulse, Wanda, Synergy Pipeline Simulator. And for HYSYS, the alternative is R, Unisim, Aspen Plus, Symmetry, and Sim Central. So as for the alternative for Olga, so there's a LiDAR flow. So you might be wondering why we are using Pipenet instead of HYSYS for the hydraulic computations. So the reason is because in HYSYS, only head and frictional pressure drop are calculated. And there is no momentum balance is taken into account. And finally, the flow and pressure in the HYSYS are governed by this equation, which is the flow is equal to K times with your square root of density times the pressure drop. So this is a very simplified pressure flow relationship, or maybe a hydraulic relationship. So this is the typical hydraulic computations employed by the most of the process simulators. So however, in Pipenet, the flow and the pressure are solved numerically using a momentum and continuity equations. So this is how the momentum equation looks like, and this is how the continuity equations looks like. So don't worry about that. So we have done some comparisons between HYSYS and Pipenet. So So consider the following scenario. So where we have a pipe dimension of diameter of 12 inch and the length of 3 kilometer or 3000 meter. So our fluid is water, and then our boundary specifications for the inlet pressure is 10 bar gauge, and for the outlet pressure is 0 bar gauge. And the flow rate is about 880 meter cube per hour, and the speed of sound is about 1380 meter per second. So this is how the setup looks like. So it's just a straight pipe, and then we just specify the pressure for the inlet and the outlet. So as the event for these comparisons, so at the time at 5 seconds, so we will ramp up the inlet pressure from 10 bar gauge to 30 bar gauge in 2 seconds. So what we will see in HYSYS. So after running the cases in HYSYS, you'll find that the pressure at different locations, which are very far apart from each other, about 1 kilometer away, they will start to increase. The pressure will start to increase at the very same time. So this is not realistic. So however, in Pipenet, the pressure at different locations increase at different time. So the time difference can be calculated based on the speed of sound of liquid and also the distance. So where we can just divide the distance by the speed of sound, which again will give us the time difference. So after we calculate this time difference and compare it against the Pipenet computation result, we find that this is consistent with what is generated using Pipenet. So hence we can say that Pipenet give a better representation in terms of hydraulic flow and hydraulic impact compared to HYSYS. So this is for the pressure, and similarly for the flow rate, you can also similar observations can also be made in terms of in terms of flow rate. You can where the flow rate increase instantaneously in the HYSYS, and the flow rate increase with a time difference in Pipenet. So you can see that in Pipenet, the flow rate will increase slower than the HYSYS case before it reaches the steady state. As for the HYSYS, it will just depends on how I think we increase the pressure in 3 seconds. Then in 3 seconds, then you will reach the desired flow rate. So I think the label here is wrong, so it should be flow rate. So here I will demonstrate a hydraulic computation using Pipenet. So let me just move my. So this is how a Pipenet interface looks like. So but I won't go through every details. But so we have a simple loading system which consists of a pump and a piping. So this is about 5 to 6 kilometer long, and we also have a shut-off valve and also another like short piping, which is about 150 meter before it sends to a tanker. So basically, we want to deliver our product to a tanker here. So through a very long pipeline before the shut-off valve, and also through a rather relatively short pipe to the tanker. So in this analysis, we want to see what happens to the system if we close off the valve in 1 second. So basically, we want to just close off this valve in 1 second. So if you can see here, so the start time so basically we will start to close the valve at 2 seconds, and then the valve will be fully closed at 3 seconds. So which means that your closing time for the valve is 1 second. So this is a very fast closing valve. So after we set up the model, then we can start running the case. So let's try to run the case. Okay, so the simulations has been completed. So now we want to look at how the result looks like. So what we are interested here is the inlet of the shut-off valve and also the outlet of the shut-off valve. So because we think that this is the most severe in terms of pressure surge and also in terms of the pressure wave. So let's look at the results here. So I just open up the graph at viewer. So where we can see the result of the simulations. So let's first look at the inlet pressure of the operating valve. So you can see that after the valve is closed, then the pressure at the inlet of the valve will increase momentarily, and then at the maximum pressure of 24 bar gauge or 25 bar gauge. So then later, then it will just then it will have some sort of a pressure wave. It oscillates at the inlet of the valve. So if let's say your piping, your design pressure for the piping is let's say about 20 bar gauge, then in this system, then it will cause some safety issue or maybe operating issues to the piping. So this is so we need to find a way to mitigate this. So as for the outlet pressure, so you can see that so there's a severe pressure waves happen at the downstream of the valve. So I think in the previous example we show you that the pressure wave can spike below the vapor pressure, but because like I said it is artificial, so that's why in here we just change the setup such that at when it reach below the vapor pressure, then it will cap at the vapor pressure here. So you then that's why you can see there's a flat line here. So this indicates that the liquid has the pressure of the liquid has gone below the vapor pressure. So if you can so this implies that so if you say if the pressure goes below the vapor pressure, so this implies that there's a vapor gap is formed in the pipe. So this can cause an issue like it can cause something like uh, your pipe rupture due to the vacuum region, and also can cause cavitations to the piping. So eventually similar, then the amplitude will decreasing over time, so as the fluid has lost all its momentum gradually. So what we want to do here, we let's say we want to try to reduce the pressure at the inlet of the valve, and also we want to reduce the pressure wave which can cause a negative pressure region here. We can cause the formation of negative pressure regions. So so let's try a case where we shut the valve slowly. So like we discussed earlier, if you slowly close your valve, you can reduce or mitigate the water hammer effects. So let's do that here. So instead of closing it in 1 second, I try to close it about 25 seconds. So I do it. So the stop time is 27. So because I want my closing time to be 25 seconds. So after I change this, then I can just run the case again and see what happened after that. Okay, so the simulations has been completed. So let's check the result and see whether our solution, our mitigation can prevent the two issues that we have earlier. So let's look at the outlet pressure here first instead of inlet pressure first. So let's look at the outlet pressure. So you can see that the pressure will still go down. So because the water has a momentum, so it will still move away from the valve body. So but if you notice that the minimum pressure achieved here is a negative 0.26 bar gauge, so which is well above the vapor pressure of the water, so which of the liquid, which is about negative 0.97. So it is well above that, so it doesn't form any vapor, yeah, here. So after the valve is fully closed, it will still generate some wave here, but this wave compared to the previous previous analysis, it is much more less severe. So this will not have uh, any issue to the pipeline. So I think so by slowly closing the valve, we can actually prevent the formation of the negative pressure region in at the downstream of the valve. So let's look at the inlet pressure of the operating valve here. So even though we close the valve very slowly, so the pressure will still go uh, above 20 bar gauge. So so this is so this, let's say if our design pressure is 20 bar, then this will not then this will cause some issue to the pipeline. So so I didn't show you here, but what you can actually do, you can actually add a liquid surge line. So and then this liquid surge line is act as some sort of like a relief valve. So when you see the pressure is exceed certain set point, then it will relieve the pressure by transfer the flow away from the pipeline. So then it can actually prevent the pressure from further increasing above the design pressure. So I guess that's it for the demonstrations. And we also want to uh, show you something more interesting. So then we post-process the result for the system with fast closing. So basically this, sorry. So we want to show you something more interesting. So we post-process the result of for the same analysis. Uh, this is for the fast closing valve where we shut the valve in 1 second and make it into animations. So this is we want to show you how does the water hammer looks like in time series. So in this slide, we are actually focused on the long pipeline. So in between the pump and the shut-off valve here. So in this diagram, the flow is represented in blue and the pressure is in green. So before the event, the flow across the valve is about 300 meter cube per hour. And also you notice that there are a pressure drop across the long pipe. So this is due to the frictional pressure drop across the piping. So just to narrate the what you expect to see when I run the animations. So you will expected to see the flow moving back and forth in between the piping. So this is due to the pressure wave generated during the event. So I will just start the animation so that you can see what happens during the water hammer event. So you can see that the water is actually moving back and forth. It will go to negative flow and then maximum positive flow it repeatedly. So which means that your flow is actually moving back and forth over time, and your pressure will also moving. So this is what how we visualize a pressure wave in the piping. So the next one is we focus on the short piping here. So at the downstream of the valve. So for the same analysis, this is without the mitigation, or I should say, this is where we analyze with the fast closing valve. So we want to see what happens to the uh, to the to the fluid in the downstream of the valve. So so similar to the previous animations, the flow rate is about 300 meter cube per hour, but the pressure drop is minimal because the piping here is very short compared to the previous piping. So this is a 150 and this is a 5,000 or to 6,000 meter. So so here's the diagram represented in the flow is represented in blue and the pressure is in green and the vapor fraction is in red. So after I run the animation, you will notice that the vapor gap is generated and collapsed from times to times right after the valve is closed. So and the size of the vapor gap will decrease over time since the pressure wave is depleted over time. So let's see what happens after I run the animation. Okay, so you can clearly see that the vapor is formed at the inlet of at the right after the shut off valve. So that's it for the demonstrations and analysis using the Pipenet. So in these sections, we would like to show you a case study. So this is for a topside water injection system. During normal operations, the water injection pump will be delivering the water to the water injection system. So this is to inject the water into the well to maintain the reservoir pressure. So during normal operating normal operations, so this valve will be closed, 100% closed, and then there is no water is allowed to go to the overboard. So what happens is when the water injection is shut down, so which means there is no longer any flow, there is no flow going to the water injection system. What happens here is the flow is diverted to the overboard. So in order to maintain the minimum flow of the of the pump. So which means that the flow FCV here will open in order to maintain the minimum flow of the pump. And for priority, we will just model the overboard line starting from the FCV to the end of the overboard line. So this is to simplify the process, and because we want to focus the phenomena happens here instead of at the pump and also at the water injections. So this is how the model looks like in the in Pipenet. So where we have our FCV here, we have our check valve, and also have our overboard line. So the water will travel from A to E before exiting the overboard line and sent to the oceans. So in this case study, we will open the FCV and see how does the fluid behave in the overboard line. So the location of each point, like A, B, C, D, E, is indicated in the diagram here, and also the flow is represented by in blue, and the pressure is represented in green, and also the vapor fraction is represented in red. So after I run these animations, you will notice that the blue line will start to move from left to right. So this is because the water is filling up the overboard line. So once the whole overboard line is fully filled, a negative pressure is formed between point D and point E. So to prove my point, so let me just play the animation and let you observe the phenomena. So there is a huge vacuum channel formed in the overboard line once the whole water is has filled up the overboard line. So if this situation is left as it is, it can cause the piping to collapse due to vacuum and also pipe cavitations. So this is a big issue if you leave it as it is. So let's see how we can mitigate this problem. So to mitigate this, we added a vacuum breaker at point D. So there's a vacuum breaker here at the point D. So this allows the air to flow into the pipe to prevent the formation of the vacuum region. And similar to the previous case, the water will be filling up the overboard line. What is different here is once the water has filled up the whole overboard line, we will see what happens later. So after we added the vacuum breaker, we can see that after the water is filled up the whole overboard line, there is no vacuum region or vapor channel is formed in the piping between point D and point E. So this is because the vacuum breaker allows the air to flow into the piping and prevent the formation of the vacuum region. And you can also notice that the pressure, the flow rate after point D, so which means after point D is increasing after point D. So this is because this indicates the total flow of the water and the air after the activation of the vacuum breaker. So which means, like, let's say the flow is around 60 here, then the additional flow is coming from the air. So by adding the vacuum breaker, we can prevent the formation of the vacuum region in the piping, and we can then there is no worries of risk of having the pipe rupture or cavitations when we operating the overboard line. Sorry. So in conclusions, performing the hydraulic computation using Pipenet allow us to identify the effects of hydraulic impact quantitatively, and we're also able to provide cost-effective solutions to mitigate these effects. So yeah, so that's the end of my presentations. Yeah, I would like to thank you again for your attention, and now I hand it back to Zihong.
Thank you, Kevin, for a very insightful session. If I could get the phone. And thank you, everyone, for attending the session today. Q&A will begin soon. Earlier, we received a comment from Johaida asking, what is the size of pipeline in the demo case? Kevin? Hello? Kevin, you're muted.
Sorry. Yeah. So yeah, just need to check that. So the diameter is about 250 millimeter.
Okay. And the follow-up comment to that is that normally we will assume SDV closes at 1 inch per second.
Yeah.
For,
So this is the basic standard. But so for some of the system, they may have a very fast acting valve. And also in this demo, we also want to demonstrate how severe is the when you close your valve too fast. So of course, in reality, you don't really close your valve very fast, but we just want to demonstrate the severity of the water hammer effects.
I see. Thank you, Kevin. I don't see any questions so far. I might have some issues with the chat. So Kevin, if you see any questions coming up,
Yeah.
Yes, Raphael, your voice is getting
questions here. There's a question from Kok On, and the question is as follows. Would the vacuum breaker and large air and water flow in the overboard dump line cause line vibration? If yes, what criterion to ensure no vibration from too large phase water and air flow?
So
can I take that answer?
yeah, sure.
So typically, when we work with Pipenet itself doesn't give any indication of vibration. But what happens is that Pipenet will allow you to get force, to get the value of force, because what happens is that you are calculating the momentum, the change in momentum, and for each point in your Pipenet provides force, like a output file in terms of force, and you can use that for as an input for other software, usually for Caesar 2. So for that, you can maybe use that to probably that will help you to see whether vibration will happen or not, some indication. But for Pipenet itself, you don't have any access to know whether vibration will occur or not. I hope that answers it.
Okay, thanks, Anwar. Ziong, are you still having problems with the chat?
I don't see any.
Okay, I'll continue. So there's a question from Shaifal, and the question is as follows. I understand that Pipenet can only be used for single-phase system. My question is whether we can use Pipenet for simulating single-phase system with multi-components.
Can I answer that as well?
Yeah.
The short answer is no. But there are, so I assume your application that you're looking at, so you probably is interested in trying to see if you have like multi-batch transport where you transport one type of fluid and then followed by a plug of another fluid, and you want to see what sort of whether the interface between those two fluids stays sharp or is sort of dispersed along the line. So the short answer is no. In Pipenet, you cannot do it. But the other alternative software for the single phase, for example, if I remember correctly, Wanda or an AFT Impulse is able to do that. They are able to do this multi-species transport in even though it's single pipeline. I think they compute the diffusion or dispersions in your system.
Okay, thank you, Anwar.
Rafil, I can see the latest question starting from Yi. So, are there any
After
others?
Shaifal, there is a question from Guru Murthy.
Okay,
Can you
I
see
can't
that?
see that. I can't.
Okay, it's okay. Let me just go through them because I can see all of them from here. So we have another question from Guru Murthy, and the question is as follows. What is the available overpressure protection available in Pipenet, like vacuum breaker, for under pressure?
So I mentioned earlier in the demo, but is I didn't show that in the demo, but we have something called like a liquid surge relief valve. So basically it's just similar to the relief valve for the gas system. So when the pressure exceeds certain set point, then it will open and then we will relieve the pressure so such that the pressure doesn't go beyond the design pressure or the set point you set for that. So there's something called liquid surge relief valve. Yeah.
Okay, thank you, Kevin. We have a question from Hairuni Safri, and the question is, can Pipenet use for pressure surge in single crude oil pipeline? I assume a single phase crude oil pipeline, and the answer to that is yes.
Yeah.
You can, as long as it's single phase. I have something coming in from someone called Yi, but I don't see the text. Okay, the text is really curious. It's white text with white background. So let me manipulate this to see. So from Yi, the question is there any general guideline when we need to do liquid surge pressure? Sorry, let me repeat that. Is there any general guideline when we need to do liquid pressure surge analysis? For example, for certain pipeline dimensions, or if it exceeds certain length or size?
I would say it's not depends on the dimension of your equipment of your piping, but rather it depends on your fluid property. So if your fluid has a very high density and also in your system you're also flowing that at a very high flow rate and the velocity is very high, so that can cause some concerns of a liquid pressure surge. So regardless of your pipe. So if you have a smaller pipe dimension, it can give you a higher velocity. So that's my answer. Arnold, do you have any input?
Yeah, if I may add that, I think there are, if you remember from Joskowski equations, there are two things that we were looking at. So if you remember from the equation, is the change in pressure equals to the density times the velocity of the fluid, sorry, the speed of sound of the fluid times the change in velocity. So the change in velocity is one thing that we will concern. So that can be either from fast closing of valve, or fast stripping of pump, or fast opening of valve, or fast startup of a pump, for example. So that is one. The other thing is the length of pipeline also relevant, because the longer you have your pipeline, for example, if you can imagine, if you have a 1 kilometer pipeline, if you do something at the end of your pipeline, say if you close the valve, for the information to be transferred back to the inlet of the pipe will take a while, and during that time you will have those pressure surge across the pipeline. So I think the main two criteria that will lead you to consider doing those kind of analysis. One is if you have high change in velocity. Two is the length of your pipe.
Okay,
Nice.
thank you, Anna. The next question comes from Hassan. What other mitigation measures are possible instead of closing the valve slower? And is it possible to model all these, I suppose, using Pipenet?
So my answer is yes. So the other mitigation measure, so other than closing the valve slowly, so you can actually have a different kind of equipment, which I mentioned in the slide. So you can actually use a accumulator, or maybe you can use the blow off valve. You can use a surge tank, and it depends whether you want to prevent a high pressure excursion, or you want to prevent low pressure excursion. If low pressure excursion, then you can try to look at the vacuum breaker and etc. So and it is possible to model this in using Pipenet. So there are features like accumulator, surge tank, and liquid surge relief valve available in Pipenet.
Thank you, Kevin. I hope that answered the question. The next one from Shanga asks, to what extent can we reduce valve closure speeds to reduce pressure surges? Instead of 1 inch per second, to what extent can we reduce valve closure speeds to reduce pressure surges?
So
Can I take that?
yeah, sure.
Kevin?
Yeah,
So
sure.
this whole idea of 1 inch per second is what typically people use, but we've been receiving some feedback. For example, for some of the customers, they're saying, since most of your SDV is operated using a spring that will close on fail position. So what happens is that if you want to close, sometimes the travel time is faster than one inch per second. So that is one thing, one point that I want to make. The other point is that to what extent, I think it depends on your results. I think another thing that I want to make a point of is consider this. Like typically, what we have is an SDV. SDV usually the CV is very big. Say 5,000 US GPM or more. So what happens is that the problems that we've been seeing is that if you have a valve closing, for the first say 50% of travel of the SDV, there will not be a drop in flow, because what happened, your CV is still big. And then you will only see the reduction in flow at the remaining, say, 10% or 20% of closing of the valve. So those are another thing that you have to take into account when you do the simulations. So hopefully from the simulation, it will tell you sort of what extent your valve needs to be closed slowly, and this will govern again by your valve size, and then the pipeline length, as well as the amount of the change in velocity in your fluid. Yeah, so that's my answer. I hope that answered.
Thank you, Dr. Anwar. The next one coming in from Azwan, who says, as suggested earlier, the wave speed term in Joukowski's equation can be controlled by having a straight pipe. How would the vertical or slanting position affect the overall delta P?
So I think I need to correct something. So basically, we want to reduce the wave speed, and then how do we reduce the wave speed? We can do it by having a shorter straight length pipe. So it's not so from that, if we have a shorter by adding more elbows to the piping, then if like you have a less shorter straight length pipe, then those elbows can actually give more frictions to the fluid, and then it can dampen the pressure waves. So basically, then how would the vertical or slanting position affect the overall delta P? So it actually depends on the relationship between the frictional pressure drop and also the gravitational potential term. So I can't really say for certain what will happen, but we will have to do some computations to identify that.
Yeah, and I just have one thing to add for that. It's actually the speed of sound of the fluid is intrinsic property of your fluids. So if you are dealing with water, you will get around 1,400 meter per second of wave speed. So that means if you do something at one point, that information will travel inside water at 1,400 meter per second. You have different speed for other fluids. For example, oil, I think it will have slightly lower or slightly higher speed. So those are sort of intrinsic value that, and in Pipenet you have to define it. So you have to key in what is the wave speed or the speed of sound or that specific fluid that we are dealing with. So I think what Kevin was trying to say is that if you still remember from what I mentioned before, the length of the pipe has an impact, because if you do something at one end, depending on the length of the piping, the other end might not feel it yet. So in order to avoid that, so that will have problematic or very bad consequences later when you want to do something at the end of the pipe. For example, if you want to close the valve. So to avoid that, in some cases you might want to have a shorter pipe or pipeline to avoid that. Yeah, I think that's my answer, just to complement what Kevin has mentioned.
Thank you, Kevin. Thank you, Dr. Anwar. Moving on, a question from Senapati, who asks, in the upstream industry, normally liquid well fluid contains some associated gas. What is the maximum gas oil ratio, say 5 or 10 or so, up to which we still need to do single phase transient analysis using Pipenet to demonstrate that surge pressure in production network doesn't exceed the design pressure while the minimum gas is present in the liquid?
My answer is I would recommend not to use Pipenet for that. So because especially because the Pipenet doesn't have the capability to do the flash calculations, and it can only use for a single phase. So because if you have some associated gas in the fluid, it actually those gas can actually like reduce your density, like and also it's more squishier rather than having like an incompressible property. So so this if you use it to, I mean, if you use Pipenet to do the liquid search analysis based on the some if with some gas in the well fluid, so I I think it will I mean it can maybe give you some weird result, so not weird result but rather inaccurate results. So I will not suggest to use a Pipenet to do some this sort of this sort of search analysis, but maybe we can explore maybe some other software that may be capable to deal with maybe two-phase or sort. Yeah, so I think that's my answer. Anything to add from you, Anwar?
Yeah. So I think as it is, Pipenet and other software can mostly handle the single phase. But I've seen some research, mainly in research where they try to implement sort of cavitations or like the pockets of gas in the system. But I have not seen any specific software catered for this. But saying, but that being said, though, like this previous speaker, previous question was from Azwan. Azwan is from Schlumberger, who provides Olga, and I think they also one of misconception about Olga is that many people think it's can only be used for slow transient event where you typically use in flow assurance. But I've seen some benchmark results where people try to use Olga for fast transient event. For example, where you have multi-phase flow like what you are asking using Olga. So I've seen some benchmark of results for this event. I think you can explore Olga for that. Yeah, I think that's my answer.
Thank you, Kevin. Thank you, Anwar. I hope that answers your question, Mr. Senapati. Next one coming from Prem. How do you enter the CV of PCV, for example, in the Pipenet model?
Yeah, so maybe I can show you that. Maybe it's not a PCV, but just a normal valve. So you can just input you can choose how you want to input your, there's different ways of input. So I think the standard way that we do is you can just straight away put the flow coefficients for the valve. So basically that's how you input the CV into the valve. So I think there are different ways to do that, but normally we will use the flow coefficient way to do that.
Okay, thank you, Kevin. Next one coming from Shaifal. Is there any alternative mitigation method to vacuum breakers for the scenario where hydrocarbon is transported, as admitting air to the hydrocarbon system will lead to safety issues?
I think the example that we show is water going to the overboard line. So the issue there is because why if it can form a cavitation there is because they at the end of the overboard line it is exposing to the atmospheric environment. So when you expose the pipeline to the atmospheric environment, so which means the pressure is atmospheric, then you can cause some vacuum there. But I believe for a hydrocarbon, let's say for your hydrocarbon oil, something like that, you won't be exposing it to the atmospheric pressure. And also I think it will normally is in the pressurized system. So I don't think there's a concern whether you will see a negative pressure here, but I don't think so that's so using a vacuum breaker of that is definitely not feasible. So but is there any alternative for that? Okay, I'm not sure. So Anwar, do you have anything for that?
Yeah, if I may add to that. I think I've seen one solution is that if you have, for example, say stabilized oil going into a tank, and if you see your piping is doing this kind of routing where it goes to a high point and then goes up to your stabilized tank. What I've seen, one of the potential solutions is to try to avoid your end of pipeline straight to see the atmosphere. So what you can do is just to put another valve before it enter the tank, such that that will give you some back pressure to avoid the low pressure on the high points at near the atmospheric tank. Uh, is that clear, Zion?
Yeah, we heard you.
Okay.
Thank you, Anu. I think that was a very, very comprehensive answer. And thank you, Kevin. We have one more question from Senapati. Does Pipenet consider valve effective closure time rather than total closure time?
I believe it's a different closing pattern, right? So if that, then it is possible you can do that. So let me demonstrate here. So you can actually do something like this. So if let's say I want to close my, here is like at 0 is at 1, and then maybe at 10 seconds is at 0.5, then at 20 seconds is at 0.2, and lastly just close. Then you can but you can actually make some change. You can make this kind of changes in order to replicate the effective closure time that you want. So I'm not sure. Yeah, so that's my answer for that.
Okay, thank you, Kevin. I don't see any further questions.
I think there's one question.
There's one question?
Yeah, from Aswan.
Yeah, I can
Yeah.
read that. So Azwan is asking, a younger me used to use a software called Natasha, Network Transient Search and Hammer. Any idea how, sorry, any idea how it is compared against other offerings? Azwan, I never heard of this software, so probably you are way older than me.
I think,
And
Azwan, I think you probably ran this off a punch card machine or something, huh?
Yeah, but to answer that, I think pretty much all of the software we've mentioned, if you're dealing with single phase liquid, the way it's being solved, if you remember the slides that Kevin was showing, there are two things basically you're solving. You're solving the one is continuity equations just to have mass balance, and then the other one is you balance the momentum. So what you have is PDEs lah. You have a couple of PDEs to be solved. So for example, in Olga, to solve this, you solve the PDE, you tackle these PDEs head on. So you basically discretize the thing. You do some finite volume or finite element system to solve those PDEs. But in all these single phase simulators, what they do is they uh, they change the PDEs into ODE. So the step is called method of characteristics, and pretty much all of the offerings out there using similar way to solve it, i.e. method of characteristics, where you reduce your PDEs to ODEs. I would assume Natasha is doing the same thing. Pipenet is definitely doing the same thing. Wanda, Stoner, SPS by DNV, the GL Noble and so on will all behave similar, but they might have other things like bell and whistles on top of it. So for example, some of the other software other than Pipenet might provide you to do the multi-patch, like multi-species fluid tracking inside the pipeline and so on. Yeah, I think that's my answer.
Thank you, Anu. Uh, I'm not seeing any updates to the chat.
There's one. What is
There
the
is
difference we will experience in choosing the CV value in the PCV or other parameters? So I guess maybe it will give rise to a different pressure drop in respect. Different flow rate in respect to different pressure drop. So because different parameters used for the CV. I mean just now when I show you, there's a different way to specify the CV. Then it may have a different equations to calculate how they relate the pressure drop and to the flow. So that's my answer for that.
Okay, I think that's all the questions we have, Zion. I cannot see any others. One, except Azwan was saying maybe I still am. I don't know. Maybe he's still using punch card in Schlumberger. Yeah.
Okay, yeah, I see that now as well. So yeah, it took a while to update. Thanks. Well then, for everyone who's still listening in, thank you very much for attending and your patience to stick around to the end. Your support is greatly appreciated. We hope to see you next session, which is 2 weeks from now. Thank you, everybody. Thank you, everybody.
Thank you.